So, every scientific theory can only be accepted by others if that theory can explain our day-to-day experiences. Now, in last class, students, we had learned about the Planck's quantum theory of radiation. Now, in the following slides, we will know why this theory is so important. Now, today's topic is photoelectric effect. Now, what is photoelectric effect? It is just an observation by scientists. So, the photoelectric effect is nothing but if you take a metal and light falls upon that metal surface, we notice that electrons can ejected out of the metal surface. This is a simple observation, and the observation is known as photoelectric effect, in which the light that falls upon the surface can be called incident light or incident radiation, and the electrons that ejected out of the surface, metal surface, can be called photoelectrons or the emitted electrons. Now, this observation was made up by scientists for a very, very long time ago, but it was the Albert Einstein who had successfully explained the observation. Now, what Einstein did, he explained this photoelectricity or photoelectric effect by the use of Planck's quantum theory of radiation, which was discussed in earlier class. So, in earlier class, we learned that the light is built up of wave packets or energy packets. These are the discrete quanta of energy called photons, and each photon will carry energy equals to h nu, where nu is the frequency of the emitted photons. Now, watch this video. So I am drawing an atom. Here is the nucleus of that atom, and there is an electron E which is revolving around the nucleus. Now, if that atom is on the surface of a particular metal, so what is going to happen now? Light is going to fall upon the metal surface. So, of course, there will be a source of light. Let the source can be sun or whatever. So, the light falls upon the electron of the atom on the surface. As a result, the electrons get ejected out of the metal surface with a certain velocity v. Now, we know that the kinetic energy of this electron can be half mv square. And of course, there is an energy of the light that falls upon the surface, that is E is equal to h nu. Here the h nu is the energy of the photoelectrons that falls upon the metal surface. Now, this is important to this is important to understand for you that every metal surface has a threshold energy, which means electrons cannot be ejected out of the metal surface if the energy provided to the electron as a light is less than the threshold energy. So, every metal has its characteristic threshold energy. So, here's the picture of the previous video. So, if h nu is the energy of the incident photons and half mv square is the kinetic energy of the photoelectrons, now if we minus the kinetic energy from the energy of the incident photons, there is an energy which is required to eject the electrons out of the metal surface. Now, that energy is called the work function. So, work function is a threshold energy, which is the minimum energy which is required to eject an electron out of the surface of a metal. So, let me repeat this again. Light falls upon the metal surface with photons equals to h nu, which is the energy of the incident light, and the electron absorbs that energy. Now, after absorbing the energy, electrons gets ejected out of the metal surface. Now this process has two parts. First, the electrons breaks the attraction force of the nucleus, and after that it attains a kinetic energy. Now, whatever energy is required to break the attraction force between the electrons and the nucleus shall be called the work function or threshold energy. And the surplus energy, after attaining the threshold energy, if there isn't more energy left, that energy can be converted into the half mv square or the kinetic energy. So we can write total energy h nu equals to h nu naught plus half mv square. So this is the formula provided by Albert Einstein. Now here is few important things to recall. First, if we increase the brightness of the light, that will not increase the kinetic energy of the photoelectrons. It will only increase the number of electrons emitted per unit of second. We can increase the kinetic energy of photoelectrons by increasing the frequency of the incident radiation. So the maximum velocity of the kinetic energy of photoelectrons depends on the frequency of radiation, not on intensity. That is, kinetic energy increases with the increase in frequency. So here are some homeworks. Light of wavelength 4000 Armstrong falls upon the surface of cesium, which is a metal. You have to calculate the threshold frequency of cesium if the maximum kinetic energy of the electrons ejected out is 6.9 into 10 to the power minus 9 joule. So you have to use this formula, h nu minus half mv square is equal to h nu naught, to solve the problem. And there is another graph. The graph is you have to draw two graphs. First, the kinetic energy of the photoelectrons versus the frequency of the absorbed photons. And the second graph you have to learn is that kinetic energy of the photoelectrons versus intensity of the light. Now here is the rules of homeworks which you must follow, and I have said this in the earlier class. Thank you. In the next class we shall learn the wave matter duality.